Thank you so much. Thank you for the invitation and the very kind introduction. So I decided to give more of an overview talk because it's always very exciting to talk about the newest results, but I understand there are people in the audience who also don't know the older results. So I will try to do it as pedagogical as possible. So I would really appreciate that if you have clarification questions, please do not hesitate and ask. I'm happy not to finish everything I prepared as long as people can understand and follow what I'm talking about. Because I see that, well, the audience is mixed. All right, so gauge theories, as Gerardo already said, it's going to be from the point of view of perturbative QFT. So it makes sense to start with, well, what is perturbative QFT? So first of all, let me start maybe with algebraic quantum field theory, and some of you would know that very well, some of you would not. So yeah, just to set the stage. Originally, this was a framework for QFT on flat spacetime, and it was developed by Hagen Kassler. And the idea is that you describe quantum field theory in terms of observables that are localized in bounded regions of spacetime. So you assign to a region O1, say the algebra A of O1 of observables that can be localized in that region. And then there are several axioms, and the first one is kind of intuitive in terms of subsystems. So if we have a larger region, then we expect to measure more observables. So that's the intuition there. So we have inclusion of algebras following from the inclusion of region. And the structure that arises from this is a structure of a net. Now, this, well, leads to maybe the buzzword nets of local algebras. So AQFT works with nets of local algebras, and there are some axioms that we require that these nets satisfy. And the two I want to mention, because they generalize nicely to curved spacetime, are causality and the time slice axiom. So causality first. Well, we know there is a causal structure in Minkowski spacetime. So if we have two regions which are causally disjoint, space-like separated, so no causal curve joining them, then we expect that the measurements, the operations performed in these two regions are independent. And this is realized by saying that the corresponding algebras should commute. And then there is the time slice axiom, which says it's something to do with initial value problem formulation. So if we have a neighborhood of a Cauchy surface, then the algebra of that neighborhood is already equal to the algebra of the full region for which we have that Cauchy surface. So in a sense, we can reconstruct the whole algebra and get the whole information from a small neighborhood of a Cauchy surface, hence a time slice. And you can see that, well, there's not much which is particularly Minkowski. There is a Cauchy surface, so we expect that the generalization is going to use spacetimes that do admit foliation in Cauchy surfaces. So the natural way to generalize this framework is to go to globally hyperbolic spacetimes. So this has been done, and the framework which this well creates is called locally convex quantum field theory. So this was already mentioned in this conference, but well, I want to talk about the particular way of constructing locally convex, locally covariant, not locally convex, locally covariant QFT models, which uses perturbative methods, so perturbative algebraic quantum field theory. So this is yet another generalization. So traditionally in AQFT, one works with C-star algebras and von Neumann algebras in particular, but here we want to go to something maybe more wild. We want to be able to work with formal power series. So want to use some techniques of perturbation theory. And let me give a few historical remarks before I go into the details of actually what we're doing. So, well, there are several building blocks that are due to various people. So the free theory is obtained using the deformation quantization, and there were works in the 2000s by Brunetti, Ditch, Frenhagen in various combinations. Then interaction is introduced using the causal renormalization approach due to Epstein and Glaser. This is much older actually than PAQFT. This goes back to the 70s. And finally, there is what I'm going to talk about today, generalization to gauge theories, which uses homological algebra. And the first result along these lines is due to Stefan Holland, and then it was generalized by Klaus Frenhagen and myself in 2011. So it already has 10 years, so you can say it's old, but we are still using it, so it's still correct, as far as I know. And maybe just one thing to mention, that there is an application of this to various approaches to quantum gravity, so that there is a way beyond gauge theories. However, I'm not going to talk about this today unless there is going to be some extra time or questions. All right, so what do we need? I said that globally hyperbolic spacetimes are good because, well, essentially by definition, being a globally hyperbolic spacetime, it means that it's a spacetime that has foliation into Cauchy surfaces. So the time size axiom makes sense. And yeah, it's a good spacetime, right? There are no closed time-like curves and things like that. And there is also the configuration space, so we have to specify what objects we want to study. So scalars, vectors, tensors, whatever. And typically, and for the sake of this talk, I'm going to assume that this configuration space is a space of smooth sections of some vector bundle. This is not too extravagant. This covers a lot of examples we are interested in. So for the scalar field, that would be smooth functions on my manifold. For Young-Mills, with the trivial bundle, this would be Lie algebra valued one forms, again, familiar. And for effective quantum gravity, I would use just metric perturbations. So again, this fits that general idea. And finally, well, this sort of sets the kinematics of the theory, and there is also dynamics, which we define using a certain modification of the Lagrangian formalism. So there is a fully covariant version of the Lagrangian formalism that we are using. I will give more details as I go ahead with the talk. So let's start with observables. So things that I'm going to associate to these local regions. And in the first instance, let me start with classical observables because these are less problematic. So I want to see them in the first instance as smooth functionals on the configuration space. And the intuition behind it is, well, you know, a classical observable, if you measure something, right, there's some field configuration, you probe it with your measurement, you get a number. So in the first instance, we would think about real valued functionals. It's convenient to actually work with complex valued things instead for the sake of quantization later on. And I require smoothness mainly for convenience because, yeah, that's definitely not harmful and allows us to already narrow things down somewhat in terms of what observables are nice. And yeah, everything is now going to be dependent on that manifold M I fix and I want to construct the theory on. But I'm not going to write M all the time because that's tedious, so I will drop M, but just have in mind that all these things work on any globally hyperbolic spacetime. Okay, so finally, localization of functionals. So I want to be able to localize these things in regions. So I want to have some notion of support. And here it is in this framework. So the support of the functional is a sort of region where the functional is sensitive to perturbations of the field in that region. So here is the formal definition. So we are looking at neighborhoods such that for all configurations such that psi is supported in that neighborhood, f of phi plus psi is different from f of phi. So really sensitive to perturbations in that region. And in particular, we can consider local functionals. So these are the most natural things to look at in quantum field theory, where we typically look at local interactions. So f should be of the following form. So it's a function on the jet bundle, and it depends only on the finite jet at a given point. So, well, I assume that most people know what the jet bundle is, but in simple words, it is a jet at point x is just the value of phi at x and the values of its derivatives up to order k. So in other words, a local functional depends only on the value of the field at a point and its derivative and its derivatives up to a fixed order. Okay, so that's locality. And there's also another nice class. So okay, so if we take products of local functionals, then we have something called multilocals. So that kind of makes sense as a generalization. And there is some much stronger requirement as well. There is another class of functionals that are much nicer, but maybe not so useful for all the physics applications, which are called regular. So they are distinguished by the fact that functional derivatives are smooth. So these are nice for kind of you know, being able to describe algebraic structures, and by algebraic I mean algebra, no functional analysis involved. Local functionals unfortunately don't fall into that class unless they are at most linear, which is relatively boring because interactions tend to be you know, higher order. So this class is sort of an auxiliary object. The physical things you want to think about are local and multilocal. And well, in a sense, they are quite singular. Local is quite singular from the point of view of quantum field theory, but you will see that we can manage those singularities and we can still construct all the algebraic structures we need. Okay, so that was observables. And now there's time for dynamics. And here we are using the notion of a generalized Lagrangian. It's not too strange. It's essentially a Lagrangian density where we introduce a cutoff. So this Lagrangian would then be a map from, well, compactly supported functions that provide those cutoffs to local functionals. And very quickly, let's look at the examples. So for the free scalar field, you see this is the usual Lagrangian density multiplied with the cutoff, integrated over the whole spacetime with the invariant measure induced by the metric. So this is somehow dealing with the problem that if we would to integrate the whole Lagrangian density without the cutoff, right? But phi is the field, it's not necessarily compactly supported. So that whole integral would not be well defined without specifying any fall-off conditions for the field. And we do not want to specify these fall-off conditions because then that restricts the kind of solutions to dynamical equations of motion. So the cutoff is necessary as a sort of, again, auxiliary step, which makes things work later on. And okay, so this is for the Young-Mills. Again, the cutoff is here, and this is the Einstein-Hilbert action if you want. Now we want to get rid of that cutoff, obviously, because the dynamics shouldn't depend on it. So here is how we do it. We use locality. So we define the Euler-Lagrange derivative of S, which I denote ds, because it is a one form, in fact, on the space of field configurations. And we do it as follows. So we evaluate S on a given cutoff, and we choose this cutoff such that, well, for a given perturbation psi, which is supported in some compact region, we choose F, which is 1 over that region, so that if we take a variation of S of F, then this variation, when evaluated on psi, doesn't depend on the cutoff. So we use the fact that for practical purposes, when we compute the variations of the action, this cutoff can be made arbitrarily large and equal to 1 on an arbitrary large region. Okay, so now the field equation is this condition, the S of phi equals 0. So this allows us to well, phrase the question of looking for a solution space of the equations of motion as looking for the 0 locus of a certain one form. So we are looking for phi's such that the S of phi equals 0. So this is the way, you know, in general, for any of these theories, we can write all the equations of motion as that condition that some one form vanishes. All right. I guess this is maybe a good time to ask if there are any questions. Okay, just giving people a chance to stop and think a bit about what I'm saying. So that is dynamics, but we're going to talk about gauge theory. So an important concept is symmetries. I'm going to use something called BV formalism. BV stands for Batalin-Wilkowicki, although the version I'm talking about is a much modified version, I'm afraid. So it has a lot of mathematics that has been developed or maybe rediscovered since the original papers of Batalin and Wilkowicki in the 70s. So here is the way I want to think about the symmetries, and you can think of sort of finite dimensional analog of classical dynamics to help you understand the general concept. So I want to think of symmetries as certain directions in the space of configurations where the action is constant. Okay, so that's the underlying idea. So here is a picture. We have these flow arrows that indicate directions. So, well, again, we want to have vector fields on the configuration space. So note that we are going one level up in the sort of abstract formulation. So we started with a spacetime M, and then we considered a configuration space E of M. So now we're looking at vector fields on E. So these are this describe the change of infinitesimal changes of field configurations themselves. So we are lifted far away from the spacetime itself at the moment. And these vector fields as functionals can also be compactly supported, multi-local, whatever you want. You can require various regularity conditions. And as vector fields do, they act on functions as derivations. So a directional derivative of a functional in the direction of a vector field X. Obviously, we take the derivative. This is no variational derivative, but that's not a big deal, right? You can think of again, finite dimensional analog, we differentiate, we take the differential and then contract with x at 0.5. So this is essentially the definition. And we can do the same with this one form of equations of motion. We can also contract it with x. And I'm going to sneak in a notation for that. So this contraction can be thought of as a map on vector fields, in fact, which I denote by delta S. And now we can say what's a symmetry. So symmetry is a direction in which the action is constant. So, well, the one form of the equations of motion should vanish in that direction. So in other words, this quantity dx contracted with x should be identically 0. So that tells me that x is a symmetry. Okay, so that's more or less the story in terms of what we want. So we have solutions to equations of motion and we have symmetries. And this whole story about the BV formalism is essentially about packaging all that information into some relatively nice mathematical structure that you can then quantize in a convenient way. So that's what we are going to do. So we are going to spend some time with classical theory trying to describe things in a nice way, and then quantization will be much simpler relatively. So first of all, we consider the space of solutions, and then, well, first, let's identify functionals that vanish on the space of solutions. And we assume that they are all of this form. So ds of phi contracted with some vector fields. In that case, the space of on-shell functionals is actually the quotient. So you take all functionals and then quotient by those that vanish on the solution space. So they describe some redundancy of the theory. Now, if the space of, well, if the space of functionals that vanish on solutions is not all of this form, well, for the sake of quantization and what I'm going to do, we can actually use this going forward as a definition. So going forward, we are going to use this quotient always as a definition of the space of on-shell functionals. So it's a more algebraic viewpoint on things. And we can now write things in a bit of homological algebra way. So this is kind of slowly sneaking in. So we have a map from vector fields to functionals, which is this delta S insertion of the one form of equations of motion. And the kernel of this map is the symmetries. So this map knows a lot. It knows about the equations of motion and symmetries. The mathematical name of this is the Koszul differential. And we can extend this short exact sequence here into something called Koszul complex. So we go from vector fields to multi-vector fields. This is the exterior algebra of the space of vector fields. And we extend this differential by using the graded Leibniz rule. All right, so if there are no non-trivial symmetries, so this space of symmetries here is just given by the image of delta S in the lower, in the higher order in vector fields, then this complex here has homology or cohomology. Well, here is homology actually only in the lowest degree. And maybe I should, can I hope I can write on things. So, okay, and try, okay, I think I will be able to use the annotation. So in case you're not so familiar with that, so let's say H0, so the zero homology of this delta S. This is going to be, so it's always the kernel divided by the image. So this is the kernel of delta S in, say, this is degree 0, this is degree 1, this is, well, there would be further degrees. So if we are looking at this situation with no non-trivial symmetries, then I can replace this just by the second exterior power of V. And then here I will just continue. So we are looking at the kernel of delta S at this point, so this arrow, and quotient by the image of delta S at this point, so the previous arrow. And if there are no non-trivial symmetries, this is the only homology which is non-trivial. The sort of higher ones are going to be very similar. I just write here. That's how I do it. Okay, yes. All right. So here I will have n, and here I will have n and n minus 1. So this is the definition of homologies. Now, why is this a good thing at all? Well, oh, sorry, I have to turn this off. Yeah, maybe, oh, okay. So just looking at, again, maybe this zero part I just mentioned. So the kernel of delta S at 0, well, this arrow maps everything to 0. So this is F, and the image of delta S at 1, so this is 1, this is 0. By definition, this is going to be functionals that vanish on shell. So H0 is actually going to be F quotient F0. So this is going to be on-shell functionals. So this complex characterizes all on-shell functionals. This is the reason why we're using it. And right, so before we move on to the more interesting case with symmetries, I want to introduce some notation. If there are any questions at this point, I will pause for a second. Okay, so vector fields, this is all kind of built on vector fields. I'm going to use a slightly formal notation for vector fields, which is very suggestive in terms of, you know, the finite dimensional analog. So if I had a finite dimensional vector field, you're familiar with that, I would write it as with some coefficients and derivatives, right? So this is d over dxi. Now this is very similar, only, well, this derivative with respect to coordinates is now replaced by the functional derivative with respect to fields, and the summation over components is now integration over the whole spacetime. So x is sort of analog of labeling the components of vector fields. Okay. So with that in mind, we can now write the action of a vector field on a functional using functional derivative. So you see, we just insert f into that derivative. So if we write things this way, we can think of those d over d phi's as generators of the space of vector fields. And in physics literature, if you've looked into gauge theories at some point, you might have heard the term anti-fields. So anti-fields are in fact nothing else but those derivatives. So we can think of them as generators for vector fields. Geometrically, they characterize a sort of basis on in the cotangent direction, right? Because these are d over d phi's. And we can introduce grading, so we can count the number of anti-fields in a given expression, and this gives us an anti-field number. So these gradings are used a lot. And there is also another cute structure, which is there is a bracket, which is called the Schouten bracket. Again, very geometrical construction. So it's something defined intrinsically. This is something that always exists for multi-vector fields. And so essentially what it does, if we have a functional, sorry, we have a vector field and the functional, then it gives the action of x as a derivation of f. And if we have two vector fields, then this is the commutator. So this is a generalization of a commutator of vector fields. And it's then extended by the graded Leibniz rule. Okay, and a nice thing about this bracket is that our differential is almost inner with respect to that bracket. It's actually locally inner. So we can write delta S as the bracket with the action, but we have to introduce the cutoff and then remove it. So it's nice that we can write everything this way. So our main sort of object characterizing now dynamics and going forward symmetries and everything is going to be the action. So this framework is really built on the idea that you construct theories from given Lagrangians. Obviously, that's somehow limiting because you might want to construct theories which are not Lagrangian, but many of the theories we care about are Lagrangian. So here we are. This essentially is the main input in terms of dynamics. The dynamics is given in terms of the Lagrangian. Okay, right. So let me very quickly say about symmetries. So again, you have to kind of buy into this homological way of looking at things. So we want to think of symmetries as some Lie algebra. In principle, this is always the case because, well, vector fields form a Lie algebra. Symmetries are particular vector fields, so they would always form some Lie subalgebra of the space of all vector fields. We assume that it's of a nice form that is characterized by some smaller Lie algebra that we understand better. So say for Yang-Mills theories, that Lie algebra would be, well, smooth functions valued in some finite dimensional Lie algebra. And in gravity, it would be all vector fields on the manifold. So this is something I will denote by S. So in physics, we are interested in the space of on-shell functionals, so functionals on the solution space, which are invariant under all the symmetries of the theory. So this is the space of what we call gauge invariant on-shell functionals. So on-shell, we already know how to characterize, and now there is also invariant. And in mathematics, there's something called the Chevalier-Eilenberg complex. I don't want to go too much into detail, but again, it's a homological way of characterizing the space of invariant. Of gauge parameters on a given functional, and you can, sorry, can you hear me? Because my internet is a bit flaky.
Yes, now we can hear you. I've lost you for a moment, but I don't know if what.
Okay, which point should I well, I can repeat that last bit, I guess. So yeah, so for the space of invariants, we use the Chevalier-Eilenberg complex. And the key thing is that, well, in degree 0, it essentially is given in terms of the action of the gauge parameter on a given functional. And one can show that, again, the zero cohomology of that complex gives us exactly what we want, namely the invariants, so functionals that are invariant under all these gauge parameters. So we have a similar kind of game to play with cohomology as we had before for equations of motion. And then we can combine these two pieces of information together in the BV complex. And I'm sorry, I'm probably going to go a bit technical at this point, but let me just give you the general picture. So we replace our space of fields with some graded manifold. If you're familiar with, well, I guess fermions are familiar for everyone. So fermions are anti-commuting variables, fields. So that's an example of having sort of odd variables in your theory. More generally, you can consider graded spaces of field configurations. And in this case, well, we have in degree 0, we have our original field configurations, and in degree 1, we have a copy of our space of gauge transformations, which is now considered to be of degree 1. And this builds the extended configuration space. And these guys should be familiar to you, maybe if you had some gauge theories encounters in the past. So these would be ghosts. So ghosts are these elements here living in degree 1. And the BV complex is now the space of multi-vector fields on that extended configuration space. So again, we have the original field configurations and the ghosts. And the BV differential is the sum of the delta, the one which tells us about equations of motion, and gamma, the one which tells us about invariance. Okay, and the magic is that when you compute the cohomology of that differential, you get exactly what you want, so the space of gauge invariant on-shell functionals. Well, that's essentially what I need from that homological story. Why did I go into all this trouble? Well, the thing is that if I want to, if I want to quantize this space, this is what I'm going to do. This can be difficult. So if the structure of the space of solutions and maybe the symmetries is complicated, then this space would be rather nasty. Now, using these homological methods, it's a nice, honest to goodness vector space, which can be relatively easy quantized using the formation methods. So I prepared my ground, and now I want to quantize this using the formation methods. Well, just one short remark. Again, we can write everything in terms of the anti-bracket. So the sort of output of that whole classical story is some extended action where we added various terms with ghosts and whatnot. And the BV operator is given as the anti-bracket with that action. And there is a nice property that this action satisfies. So this is kind of by construction. It's called the classical master equation, which says that the bracket of the action with itself vanishes. Okay, so now a complete change of pace. So if you got lost in part 1, then you can come back because this is going to be slightly different, actually. So this is a maybe parallel story to what I said. This is in general about the formation quantization, and I'm going to start with the scalar field. So this tells the story of how to quantize things in general in PA QFT. So let's start with the scalar field, because gauge theories is not going to be much worse, in fact. So here the space of configurations is smooth functions on the manifold. And we have the following. So the equations of motion are very simple as well. So they are given in terms of the Klein-Gordon operator. And the Klein-Gordon operator has, well, assuming that M is globally hyperbolic and for, well, P of this type, so Klein-Gordon operator, but also things that are sort of wave operator plus lower order terms, we have retarded and advanced green functions. So they are green functions, so that's one thing, but they also have nice support properties. So the retarded one propagates the support of the initial data to the future and the advanced to the past. And the difference is the Pauli-Jordan function, which is actually a distribution, also known as the commutator function. So delta R minus delta A. Classically, we can use it to define a Poisson bracket. This is yet another bracket. There are many brackets in this story. It's different from the bracket before. So we take derivatives of the arguments and then contract it with delta. And oh, maybe I should say it at this point. So this is fully covariant. So the green functions and this delta, they are fully covariant objects. We don't need to foliate anything. Everything at the moment is off shell, meaning that F and G are functionals on the whole space of configurations, not on the space of solutions. So this bracket is first off shell, and second, it's fully covariant. So it's a fully covariant Poisson bracket. This is due to Pyers. Okay. And if we now go on shell, then this bracket would be equivalent to a canonical bracket that we would construct by using the explicit foliation with Cauchy surfaces. So this is equivalent to the canonical bracket. So I'm saying this because, well, there is always the slogan that there is a problem with using, well, constructing a Poisson structure in a covariant way. Well, that problem has been solved a while ago already. So this is a very convenient structure to use because it uses only covariant information that you have on your spacetime. So this is the covariance bracket. And then we use deformation quantization to define a non-commutative product. So this is our quantum product. Now F and G are sort of upgraded to quantum observables. And here we modify our delta, so the commutator function a bit. So we upgrade it to the 2-point function. So W here is used in this deformation, and it has anti-symmetric part given by this commutator function, and it has symmetric part, which is added to it to make the singularity structure better. So this W has to satisfy the certain wavefront set condition, which makes it a 2-point function of a Hadamard state. So this well, connects to Hadamard states. So with that object, we can define this product, and that already gives us the free theory. So you see the quantization, well, it's relatively straightforward conceptually. You just need this input of a 2-point function of a quasi-free Hadamard state, and then you get the formation, you get the star product. And again, works very well on curved spacetime. At this point, different choices of this star product actually lead to equivalent algebras. So I had to make a choice of a Hadamard state at this stage, but different choices of Hadamard states leads to equivalent isomorphic local algebras. So that's good. So the algebraic structure is actually independent of that choice. Okay, so that's the free theory. Now, for the interacting theory, let me briefly restrict myself to regular functionals so that I don't have to talk about functional analysis too much. So I need yet another propagator, yet another distributional kernel, which is now called the Feynman propagator. And the name is justified. This is the sort of curved spacetime analog of the Feynman propagator. It looks very similar to the two-point function, only instead of taking the difference between advanced and retarded green functions, I take their sum. It also has this dependence on h. So it's a sort of Feynman propagator corresponding to my choice of a state. And if I was on Minkowski spacetime, this time ordering here would correspond to taking a convolution with the Gaussian measure in path integral. So this T is actually encoding the combinatorics of the path integral. And for me, it's useful because it defines yet another product. So we had the non-commutative star product, and now we also have a commutative time-ordered product. So this is given in terms of this time ordering. And it's time-ordered because it's, in fact, using the support properties of green functions. This is the time-ordered version of the star product. So it coincides with the star product if the supporter put in the correct order. All right, so using that, I want to introduce interaction into the theory. So I'm going to do some sort of analog of the Gelman law formula. So I take an interaction functional and I define something called the formal S matrix, which is a time-ordered exponential. And now the interacting fields are given in terms of something called the Bogoliubov formula, which again bears a lot of analogy to the Gelman law formula. So if you look at this here, so very roughly, right, it would correspond to taking the path integral of this. I should maybe correct that. So this would be the Gaussian measure and then normalized by taking just the path integral of the interaction itself. Okay, so this is just in that language, this is just insertion of f into the path integral. So again, we have an algebraic rendering of that formula.
Kasia, you have 2 more minutes plus the 10 minutes for questions, okay?
Awesome, thank you so much. Okay, so I introduced the interaction, so maybe it's time to wrap up. So that's the general story of how to construct interacting theories for the scalar field. Yeah, so just to finish, let me tell you what happens with gauge theories. So as I said, we have this extended action that we constructed, well, with all that homological business. But then we can run this whole machinery of deformation quantization on this extended action, completely ignoring where it came from. It works exactly the same way. The point is that, well, we have to arrange things in such a way that, again, the free theory, so the bit that we know how to quantize, gives us normally hyperbolic equations of motion. So we have to do some gauge fixing along the way. And then we can use the exact same framework. So I'm going to skip maybe the more technical details. Yeah, so again, we have the linearized classical BV operator given as the anti-bracket with this free action, which is nice and well behaving. One thing I want to mention to maybe finish is, well, we had the classical master equation in the previous story. Here we have something called the quantum master equation, which essentially corresponds to, well, the statement that the S matrix, the formal S matrix, is invariant with respect to this linearized BV operator. And if we do the calculation, this this object can be written in a nice form, and the expression in brackets is what one usually sees as the formulation of the quantum master equation in the literature. So we have the classical bit, which is the classical master equation, and we have a quantum correction, which is called the BV Laplacian, and it's, well, kind of Laplacian where you take the derivatives with respect to fields and corresponding anti-fields. Okay, so this is then the standard form. And similarly, we can also define the quantum BV operator, which is a deformation of the BV operator using, well, in the free theory, just the time ordering map, and in the interacting theory using this Bogolyubov map. So now these operators are going to be also deformed. So you see in the free theory, you have the original one plus the quantum correction, and then you recover the quantum observables by taking the cohomology of these new deformed operators. Okay, since I'm running out of time, let me now maybe summarize some work in progress as well. Oh, that's not in progress anymore. Sorry, I should have updated the last slide. Currently, I'm working with Romeo Brunetti, Michael Dusch, and Klaus Frenhagen on trying to understand the sort of finite non-perturbative C-star algebraic version of that. We have a paper on quantum Noether theorem, which is now actually on the archive and soon to be published. But we are also trying to understand the finite version of this BV story that I was talking about, and also I'm trying to understand generalizations to theories with boundary together with Michele Schiavina. So this is still kind of a thing that's being researched. So there is a lot of work going in that direction, but this is a discussion for another time. Thank you so much for your attention.
Thank you very much for such a great talk, Kasia. We have now some time for questions. So please, can you raise your hand, those that want to ask something? Okay, for the moment, I do not see any raised hands, but I have a question myself. When you introduced this definition of symmetries, you did not distinguish among gauge symmetries and let's say global symmetries. Could you comment on?
Oh yeah, I did it you know, in a very sneaky way. So let me go back to this formula. That's a great point. So oops, here. Okay, so these vector fields, first of all, I assume that they are compactly supported. So that is, well, that actually excludes global at this point. So it's local and well, I guess there is a, well, yeah, gauge symmetries, maybe it's just a terminology issue. What we mean by that here, to be very precise, these are local compactly supported symmetries. So a local in the sense that they act locally on fields. So that is, well, one of the meanings of a gauge symmetry, for sure. So yeah, this is essentially put into, the restriction to vector fields, which are both local and compactly supported.
Okay, I see. Thank you. We got another question from Jafet Sanchez. Please unmute yourself and ask.
Hello, thank you for your talk. Well, I have a very maybe naive question. What does multilocal means? And also you said that, well, if we like that this can be used for quantum gravity. So if you maybe can say something about it shortly. Thank you.
Sure. So multilocal is products of local. So say, bilocal would be a product of two local functionals. So say, right, just to give an example. So you would have, say, phi squared of x. This is, yeah, not used to this anymore. And here some compactly supported test function, and then multiplied with, say, phi cubed of y, and another smooth compactly supported function. So that's multilocal. So this kind of depends on fields at two different points.
Okay.
With gravity, yes. So in a sense, you can think, well, first of all, you can just start with the Einstein-Hilbert action, right? And then we can treat it as a theory of the metric perturbation. So we say that G is G0 plus H. We fix the background spacetime and consider H as first the classical field and then the quantum field of the theory. So this approach is effective, it's perturbative. So in the end, we can think of this as a coupling. And then we are looking at things which are of fixed order in H and fixed order in, oh dear, H bar. So we are only kind of building effective theory this way. So yeah, well, the same procedure follows, right? We can compute the equations of motion, and the symmetries here are going to be, well, all vector fields, so all infinitesimal deformable. Well, actually, no, maybe all compactly supported vector fields because of that restriction. But yeah, so that's the idea. And then at the end of the day, we have to show that, well, we are independent of that splitting, so some sort of background independence. So this has been analyzed in the paper of Brunetti, Frenhagen, and myself from a few years ago. Well, yeah, it has perturbative quantum gravity in title. Yeah, so we worked out all the details and applied this formalism into that case.
Okay, thank you.
Thank you for your question. So do we have any other questions, please? Don't be shy. Antonio, please.
Yes, thank you, Kasia. It was a very interesting review, very enlightening for people like me that are not very familiarized with the language used in this algebraic approach. So my question is maybe a bit more general, but so the question is whether this formulation for interacting gauge theories could give light to some unknown parts of QFT and Minkowski that generalize to curved spacetime, for example, the renormalization group. Could this be a good way of proving this kind of structure that you have there, but maybe it's not well defined in more generalized spacetimes?
Yeah, so actually, for this whole story, there is a notion of renormalization group. So there's a paper by Brunetti, Deutsch, and Frenhagen on renormalization, perturbative algebraic quantum field theory and renormalization groups. It's formulated on Minkowski, but all of the content generalizes. And there are several papers of Brunetti and Frenhagen on renormalization of curved spacetime. So yeah, I guess I think it's worth maybe sketching this, because that's a very good question. So we have this S matrix, and the Epstein-Glaser framework allows us to construct those time-ordered products for local interactions. Now, Epstein-Glaser doesn't give you a unique answer. So you can, for given interaction V, local interaction V, you can have different possible time-ordered products. So this ambiguity is related to the fact that you have singularities. So this is the renormalization freedom. And you have, so this freedom is kind of characterized by finite renormalization maps that take local functionals to local functionals, and these have to satisfy some properties. So this is called Stückelberg-Peterman renormalization group. So that's the renormalization group we're talking about. So yeah, everything is on general manifold. So this is, well, general globally hyperbolic manifold. And then there's the main theorem of renormalization, which tells us that if we have another prescription for these time-ordered products, then it differs from the, not really good with these. It differs from another such prescription by applying this renormalization map. Okay, and you can think of applying this renormalization map as adding finite counter terms. So the cute thing about it is that you can do all that story fully covariantly, working with this covariant time-ordered product and covariant star product. So you can bring things which normally live on Minkowski spacetime also to the curved spacetime environment, so to say.
Okay, thank you.
Thank you for your answer. So we have to move to the next speaker. We thank again Kasia Rejzner for such a wonderful talk.